Hi, this is Dr. Doobie with another very interesting tutorial on separation processes. This one is how to analyze mathematically a column with many stages. Here is the problem statement. 100 moles per second of a saturated liquid consisting of 45 mole percent hexane and balanced heptane is fed to the fifth tray of a 10-tray distillation column equipped with a total condenser and a partial reboiler. The column operates at 2 atmospheres. The distillate flow rate is 40 moles per second and the reflux ratio is 2. Determine all flow rates, compositions, and temperatures. When we're talking about 10 trays, a reboiler, and a condenser, that's a lot of variables. It's inconvenient to use the brute force method like we did with the three-stage column. So we're going to have to use another method, the Lewis method, which is a stage-by-stage calculation. Let's start with a picture of the entire column. This is the column represented by a rectangle, and the little dots in here represent the trays in the column. We feed someplace in the column, typically towards the middle of the column, but not always. The vapor flows up the column and liquid flows down the column. The vapor leaves the top tray and goes into a total condenser. It's a heat exchanger that removes heat. And I put the vapor as red. And it condenses the vapor into a liquid. And we'll assume usually that this is a bubble point liquid or saturated liquid. The liquid here is split. Part of it is taken as a distillate, which is our top product, rich in the light components. And the other part of it is returned to the column as reflux. The liquid leaving the bottom of the column goes into a partial reboiler, which adds heat to the liquid, partially vaporizing it. And the vapor goes back into the column as boil up and becomes the vapor rising through the column. And the unvaporized liquid is now our bottom's product. It's rich in the heavy component. Now, typically, the feed is specified, not only the flow rate and composition, but its thermodynamic state. For instance, it might be specified the feed is a saturated liquid. The column's number of stages or trays is specified, and where the feed is placed, which tray is fed to. In addition to this information, 2 other pieces of information will be needed to analyze the column. It could be the distillate flow rate, it could be its composition, it could be the reflux ratio, it could be the bottom's flow rate, the ratio of the bottoms to the boil up, the bottom's composition. All these things are possible variables that could be specified, but 2 more, in addition to the feed and column, are required to solve this problem. Here is a PFD of the top of the column. We have the total condenser, and we have tray 1. There's a vapor going from tray 1 to the total condenser, and a liquid coming out, assuming that's a saturated liquid. And it's split in 2 as we discussed before. In a stage-by-stage calculation, we start by solving for the temperature, flow rate, and compositions of the streams associated with the total condenser, and then work our way down the column. Let's first start by labeling the streams associated with the total condenser. I'll use green for variables that we have specified, and so we know that the distillate flow rate was 40 moles per second. So I can write that down as green, known. Let's see, there's nothing else that I know about the streams coming into or out of the total condenser. So I'll put in red the variables that we don't know. We have the vapor stream, which we'll call V1. It's labeled after the stage that it comes from, so it's tray 1, so we'll call this V1. And it's got a composition Y1. The distillate will have a composition XD. And the reflux will give that the symbol L0, and it has a composition also XD. And actually, the vapor coming into the condenser has to have the same composition as the distillate, because no composition change occurs as the condenser changes all the vapor to liquid. We also don't know the temperature of the condenser, so we'll have to calculate that. I'll call that T sub C for condenser. The next step is to conduct a degree of freedom analysis. So we look at the unknowns. I'll abbreviate that this way. And I'll put parentheses here for how many we have. We'll find that out. We have V1, TC, L0, and XD, the distillate composition. So we have 4 unknowns. The equations hopefully we'll have 4 of those. We have, normally you'd think we'd have 2 material balances, but because the composition of the vapor and liquid is the same, we really only have 1 material balance. The component material balance is not independent of the total material balance. And so we'll have the total mole balance. We have one equilibrium relationship, which is the bubble point equation that relates the composition of the distillate to the temperature of the condenser. So we have the bubble point equation. And we have a process specification. And that was the reflux ratio that related L0 to D. That's just 3 equations. So we don't have enough information. And actually, if you look at any stage in this column, there's not enough information to solve any one of them. So at this point, we have to make a guess. The idea is we'll make a guess for one of the variables. In this particular situation, let's guess XD. And then after we do the stage-by-stage calculations, we'll find out if the bottom composition that we get from the stage-by-stage calculation is the same as the one that we would get from an overall mole balance around the column. So now we can write the equations and solve for the total condenser. We have our total mole balance, and that is V1, the stream that comes into the condenser, is equal to L0 plus D. We have our bubble point equation. That will be the mole fraction of hexane times the K value, and we'll call this Kc for condenser and 6 for hexane, plus the mole fraction of heptane, which is 1 minus XD, times its K value in the condenser, we'll call it Kc7. This is equal to 1. The process specification, which was the reflux ratio, is L0 is equal to R, the reflux ratio, times D. And finally, we guess the value for XD. Actually, we didn't guess yet. Let's do it now. Let's guess that XD is equal to 0.8 moles of hexane per mole. We can put these equations into solver to determine the unknowns, but it'll be more efficient if we write out these equations for each of the stages and let solver determine the variables all at once. Now let's look at tray 1. We'll speed things along here by writing out the equations without doing the degree of freedom analysis. Trust me, it will work out. So for the tray 1, we already know the streams above the tray from the analysis of the total condenser, V1, L0, and XD. But we don't know the variables associated with the streams below the tray or the tray temperature. So for the equations, we have the total mole balance, V2 plus L0, those enter the tray, and V1 and L1 are the streams leaving the tray. The hexane mole balance is just the flow rates times the compositions, the mole fractions. Those are the two mole balance equations that are independent. We also have the hexane equilibrium, which is just y equals kx. In this case, the k value is for the first tray. Each tray and the condenser, etc., have different temperatures, so we have to distinguish these. And that's for hexane, so we'll write 6 and times its composition. For heptane, we'll just say its mole fraction, which is 1 minus the hexane mole fraction, is equal to K17 times the mole fraction of the heptane. Oh, that's 4 equations, but we have 5 unknowns. 1, 2, 3, 4, 5. So we need another equation. This is where the EMO, or equal mole overflow assumption, comes into play. We will assume that unless something is being put into or taken out of a tray, that the flow rate going into the tray is the same as the flow rate leaving the tray. And we could do that for the liquid. L0 is the same as L1, or we could do it for the vapor. And in this case, we will do it for the vapor. V2 is equal to V1. The reason being that down the column, we're going to be adding some liquid feed, which will change the liquid flow rate at the bottom of the column. To avoid that, we'll use the vapor flow rate, which is consistent all the way through the column if EMO is valid. And so the other equation will be our equal molal overflow assumption, which is simply V2 is equal to V1. And now we have 5 equations, 5 unknowns, and we can solve for the streams below tray 1. And we continue this all the way down to the feed tray, which will be a little bit different. So I'll do the analysis for the feed tray. So now we get down to the tray 5, which is the feed tray. And the difference here is we have the feed stream going into this tray. So there's an extra stream. We have vapor leaving and liquid leaving. And we also have vapor coming in from the stage below, the tray below, and we have liquid coming in from the tray above. So the total mole balance is the streams coming in, V6 plus L4, but also plus F, and then minus the streams leaving, V5 and L5. The hexane mole balance will be similar. Now we just take the flow rates and multiply by the mole fraction. And the equilibrium relations for hexane and heptane are the same type of thing. Again, the K value is specific for that fifth tray and for the component, hexane or heptane. We also employ EMO, which is that the vapor flow rate coming into tray 5 is the same as the vapor flow rate leaving tray 5. Now here you can see why we don't do this for the liquid, because L4 is different than L5 because we're adding this liquid feed. And finally we get to the partial reboiler. We usually label the vapor flow rate coming out of the partial reboiler as VR with composition YR. The liquid leaving the reboiler is called the bottoms, and so we symbolize that B, and XB is its composition. And we also have the liquid coming down from stage 10, L10 and X10. Now, these variables in green are known from the analysis stage 10, so the only unknowns here are the bottom flow rate and the composition. So for equations, we just need the total mole balance to get B and the hexane equilibrium equation to get XB, because it's in equilibrium with the vapor coming out of the partial reboiler. Now you might be wondering, did I cheat when I guessed XD was equal to 0.8? Not really, because now we'll look at the overall mole balance. Does the amount of hexane that came in with the feed equal the amount that leaves with the distillate and with the bottoms? If not, we just go back up to the top of the column and make a new guess for the distillate composition and do the whole process again. Here is the spreadsheet solution, which you can download with the tutorial. It's always best to do that and look at each cell individually. Make sure you understand exactly how the calculations are being done. But here we have our specifications. The distillate flow rate is 40. The reflux ratio is 2. And I'm guessing XD will be 0.8. I don't know that. We'll find out. We have a row for each stage. We have the total condenser, the 10 trays, and the partial reboiler. We are feeding, F is sent to tray 5, and it has a composition of 0.45. This column here has the liquid flow rate leaving each stage and the composition of that liquid. This column has the vapor flow rate leaving each stage and its composition. The temperature is just a guessed number. I knew the range should be something like between 90 and 120 something. So I just made these guesses. These are just numbers. And these are the K values based on this temperature and the pressure, which was 2 atmospheres or 1520 millimeters of mercury. And so we have K for hexane and K for heptane at these temperatures. Since the liquid composition at the condenser is known, or guessed anyway, we've used the bubble point equation to check to see if this temperature is correct guess. I put this is Kx plus Kx minus 1, so it should equal 0 if it's correct. Well, it's not, so it'll have to be iterated. For the others, we use the dew point equation because they will look at the Y value and determine whether the temperature is a correct guess based on the Y value. Now the liquid flow rate coming out of the condenser right here, that is based on the distillate flow rate and the reflux ratio. So R times D is 80. The composition of that stream is just what we guessed, XD. And the composition of the vapor leaving tray 1 is the same as the distillate composition. So that is just called from the cell here. The vapor flow leaving tray 1 right here is just the liquid leaving the condenser, 80, plus the distillate flow rate, 40. All of the other vapor flow rates are just based on the equal mole-out overflow assumption. So we just copy the 120 on down the rows. The liquid flow rates are all calculated based on the total mole balance. When we get to the feed tray, we see that the flow rate goes up by 100 moles per second because the feed was a saturated liquid, which we assume goes entirely into the liquid stream. Not necessarily true, it's an approximation, but we'll go with that. At the reboiler, we take out 60 moles per second as liquid, leaving 120 moles to go back up to the column as vapor. Calculation of the mole fractions is a little bit more complicated. All of the liquid phase compositions are based on equilibrium with the Y values. The Y values are calculated based on a hexane mole balance, which I'll show you in a second. So the liquid leaving tray 1 is in equilibrium with the vapor leaving tray 1, which means that it's calculated as Y divided by K, because it's Y equals Kx, so X equals Y over K. Now that's only true after this dew point criteria has been satisfied based on this Y value and the temperature. Now, once that's calculated, the Y value for the vapor flow rate here, vapor composition here for tray 2 is calculated based on a mole balance around tray 1. Why? Because if you do a mole balance around tray 2 to get the mole fraction of the vapor phase from tray 2, you wind up with a circular reference. And so it has to be based on the mole balance of the tray above it. Let me show you that. So we find the mole fraction of the vapor leaving tray 2 using the mole balance around tray 1. So around tray 1, the hexane mole balance is what comes in from the liquid coming in from the tray above, plus the vapor coming in from the tray below, which contains our Y2, plus any feed that goes into that tray. That's equal to the liquid leaving that tray 1, plus the vapor leaving tray 1. Now, we solve for Y2 here and divide through by V2. Now, all these things are already known. And so we can calculate Y2 based on that mole balance. And that's continued all the way down the column, always being determined from the mole balance about the tray above it. So here's the order of calculations. We know the composition of the distillate, and so we use the bubble point equation here to iterate for the correct temperature. Now, we know that the vapor composition coming into the condenser from tray 1 is the same composition as the distillate, and so we use the dew point equation to iterate this temperature to find the temperature of the tray 1. Once that's done, these K values should be correct. And now the liquid composition here is just the vapor phase composition divided by the K value. Then This composition, the vapor phase coming out of tray 2, is calculated based on a mole balance that only involves these streams and this flow rate. Then the dew point equation is iterated until this temperature is correct based on that mole fraction. Then the X value, the liquid phase composition leaving tray 2, is in equilibrium with this Y value using the K value. And that continues all the way down the column. Now, in Solver, we'll ask it to go ahead and iterate all these bubble point and dew point equations to get the correct temperatures, and then these other calculations will be done automatically. So here's the spreadsheet after that first iteration. Notice that all of the criteria here are satisfied. So these temperatures are correct. But wait a minute, look at this. We've got negative mole fractions. How is that possible? Well, remember, we made a guess up here of 0.8. It's probably not correct. And so what we got to do is come down here and look at the mole fraction that we would get from an overall mole balance. It's 0.217. If we have a distillate flow rate of 40 and a distillate composition of 0.8, then we know that the bottom's flow rate must be 60, which leaves only one unknown in the overall material balance, and that would be XB. So what we can do is say, okay, the overall material balance here, the composition, that should be XB, by the way, the composition here should be the same as we get from the stage-by-stage calculation, or we've made the wrong guess. So, Solver, go back and change the value of our distillate composition and keep doing this calculation over and over and over again until the difference between the mole balance, overall mole balance composition and the stage-by-stage composition is 0. So now Solver has done this, and it's gone back and changed the distillate composition until both the criteria here are solved and this criteria is solved, that the overall mole balance shows that the bottom's composition is the same as achieved from a stage-by-stage calculation. And we have a bottom's composition of 13.1% hexane and a top composition of 92.8% hexane. And now, if you want to know the temperature of any tray, it's here, and the composition of the liquid and vapor of any tray. Here's a little bonus. I've plotted on the XY diagram the compositions of the streams leaving each stage and the compositions of the streams passing between stages. The streams leaving each stage are here on the equilibrium line. They're in equilibrium because they are leaving each stage, and that's the assumption of an equilibrium stage. The streams passing between stages are plotted here. And the interesting thing is, if you look at these compositions here high up in the column, they seem to be on kind of a straight line. And if you look at the compositions of the streams at the lower part of the column, they seem to be on a straight line. Here I've connected those points with lines, and you notice that they form a sort of stair-step pattern. That's very interesting. Here is the same plot, but I've connected the passing streams with a straight line above at the top of the column and those at the bottom of the column, and they do seem to fall in a straight line. This gives us a hint about a graphical technique that we'll learn about later called the McCabe-Thiele method, which can also be used to analyze distillation columns. These are called operating lines and are based on a material balance around the column. So there you have it. That's how to analyze a large column using the Lewis method.